Welcome student. Our today lecture is on processor design. These are the contents of our today lecture: processor design, processor organizations, general, register organization, stack organization and addressing mode. So first, what is the processor design? The processor design is the design engineering task of creating a processor, a key components of computer hardware. It is subfields of computer engineering, that is design, development and implementation, and electronics engineering, that is a fabrication. The design process involves choosing an instruction set and a certain execution paradigms like as a VLIW and or RISC and result in the microarchitectures which might be described in VSDL and Verilog. For microprocessor design, this description is in manufacturers implying some of various semiconductor devices, fabrications, processes and resulting in the die which is wounded onto a chip carrier. The chip carriers is the shoulders onto or inserted into a socket on printed circuit board that is known as a PCB. Now processor organization. Basically processor is organized in two ways. First one is the register organization and second one is the stack organization. So what is the register organization? Basically register organizations is used to manage a processor using the help of the registers, and in which we text the certain registers and the content of these registers are loaded in some multiplexer, and we know that the multiplexers do works on many input and one output. So according to the required register data, we provide the control selection bit of the multiplexer and we get the required data from the multiplexer, and getting this data from the multiplexer, we pass this data into the corresponding ALU unit, and this ALU unit perform required arithmetic logical operations, and after performing these operations the result is sent again to the destination registers. So that is basically block diagram of register organization. The set of registers in the computer are connected to the ALU using bus and multiplexers. Here we see in the register organization there are 14 bits which are known as a control word bit or control word specification. Two source registers are used selecting select A and select B. So select A and select B are basically is outputs of the multiplexer A and B. A destination register is selected, that is known as a select D, and we basically perform the operations using these 14 bits control units, and according the binary value of these OPR bits we decide which operation we have to perform on the data. The remaining 4 bits of the control words can be used to specify the following ALU operation. The register can be specified using 3 bits each as follows. Here we give the binary codes for selecting the required register. If we give the 000, then in selecting A we is input and in selecting B input. So when we want to select the register A from multiplexer A, or in other words we want to get the input from the register A, in the multiplexers, through the multiplexer, so we have to give the binary code 001. So this 001, when we give this 001, this 001 basically denote the contents of register R1. So binary code bit value 001 denote the register R1 and 010 denote the register R2, 111 denote the register R3, and similarly 100 denote register R4, 101 denote register R5, and 110 R6, and all bits with X 11, it means triple time 1 denote the register R7. So basically these binary codes are used to select the required registers, and according the bit value of these bits we select the corresponding register. Next, basically we use the operation table, and these operation table basically used to determine the operations bits, and according these binary bits we define which operation we have to perform on the data. If all bits are 00, it means we want to perform the transfer operation, and it is abbreviated with TSFA. And if 1001 bit is given, then we can say that operation bits are 0001. It means increment operation we have to perform, and its abbreviation is INCA. 0010 operation bits is taken, it means we have to perform the addition operation between the contents of two registers. If we are taking 0011, then using this bit we determine that we have to perform the subtraction operation between registers. And if we take 0100, it means we have to perform the decrement operations on the content of register A. And if 0101 bit is taken, then we can say that we have to perform the AND operation between content of register A and B. And it is denoted abbreviated with AND. And if 0110 is used, then we have to perform the OR operations between the content of register A and B. And if we are taking 0 triple times 1, then we can say that we have to perform the XOR operation between content of register A and B, and it is abbreviated with symbol XOR. If we are taking operation bits 100, it means we have to make the complements on the contents of register A, and it is denoted by COM A. We are taking 1001, then it means we have to perform the shifting right shift operation on the contents of register A, and it is denoted by SHR. And 1010 bits are taken, then it means we have to perform the shift left operation on the content of register A, and it is denoted by SHL. So to perform the register organization, and we take some example how we perform the operations using this organization. Suppose we have to perform R3 equals to R1 plus R2. So when we want to perform this operation, or we want to execute this instruction, then we have to select first. We have to select in the selecting line A001. It means we have to take the content of register R1 into the multiplexers. So 001 is used to place the content of register R1 into bus A, and second register is R2. It means we have to select the bus B. So we have to select the binary bits of select B to 0, 1, 0 to place the content of R2 into the bus B. and basically we have to perform the addition operation. So we have to take the operations bit 10010, and this bits denote that we have to perform the addition, arithmetic addition operation between content of A and B. Now we select the destination register 011, because our destination register is R3. We have to shift the result of our addition of R1 and R2 into R3. So R3 is our destination register. So we have to select D bit to 011. Place the result available on the bus in R3. Now, second organization is stack organization. So first we will discuss what is the stack. A stack is a storage device that stores information in such a manner that item stores last is the first item retrieved. In other words, we can say that a stack work on the principle of last in first out. The operation on a stack can be compared to stack of tray. The last tray placed on top of the stack is the first to be off. The registers that hold the address for the stack is called stack pointer SP, because its value always point to the top item in stack. The two operations are performed on stacks. First one is insertion and second one is deletion. So insertion operation is known as a push operation, and deletion operation is known as a pop operation. Here basically SP is a stack pointer, and basically this SP denote the current situation of the stack. It means it denote what is the current situation or what is the current position of a stack. The stack is empty or a stack is full, that is also determine the value of SP. Here we use the 64 address stack. So each block have the 6 bit and it is addressed by 0 to 63. So this is the 64 bit addressing stack. Here first we said use the two flip flop. First is full and second is empty. In starting, when there is no any data in the stack, we set basically empty 0 and full 1. So it denotes that our stack is empty. Now these are some contents regarding to the stack. In the above mentioned stack, 64 word stacks, the stack point the contains 6 bit because 2 power 6 denote the 64. So since SP has only 6 bits, it cannot exceed number rather than 111111 in binary, and this value of this 1111 denotes the 63, and we did use basically 0 to 63. It means 64 blocks in the stack. When the 63 is increased by 1, the result goes to 0. Since 11111 plus 1, it denotes 0000001, and we know that we always take the 6 bits, so we have to consider only the first 6 bits. So our result is always goes to 0. It denotes that our stack is our flow. But SP can accommodate only the 6 least significant bits. Similarly, when 0000000 is decremented by 1, the result is again get 1 1 1 1 1 1. The 1 bits register full is set to 1 when the stack is full, and 1 bit register empty is set 1 when stack is empty of item. So we can say basically when empty or stack is empty, then we can say that empty flip flop value is 1. Here we use the other register DR. DR is the data register that hold the binary data to be returned to or read out of stack. Now here we text the push operation because we know that there are two basic operations performed on the stack, push operation and pop operation. So we take some steps regarding to the push operation. Initially SP is cleared to 0, empty is set to 1 and full is cleared to 0, so that SP point to the word at address 0 and the stack is marked empty and not full. So these are three content. When at the case of the empty, we basically SP denote set with 0, empty set 1 and full is set with 0. That denote that our stack is empty. If the stack is not full, a new item is inserted with push operation. The push operation is implemented with following sequence of steps. First, we have to increase the value of stack pointer by 1. So SP goes to SP plus 1, and after getting this increment, we put M of SP with set with DR. DR is basically data register through which we insert the data in the stack. And after doing that, if we get the SP 0, then at the time of the pushing operation, if we get SP equals to 0, then we set the flip flop full with 1, check if stack is full, and we set empty 0 to denote or mark the stack is not empty, it means or stack is full. Next operation is the pop operation. In this operation, we basically delete the data from the stack. So there are some selecting steps. First, we have to select the stack top, and content of stack top is put in DR register, and after selecting or pop outing the element, we always reduce the value of SP by 1, and in this operation we again check if SP equals to 0, then we set empty 1 for the check stack is empty, and we set full equals to 0. That denote that our stack become the empty, and in the case of the empty, we never can perform the pop operation. Now our next point is addressing mode. So what is the addressing mode? Basically, addressing mode is a technique that is used to determine the actual address of the operand. So the addressing mode is a way that show how is the address of an operand specified and how are the bits of an instruction or organized to define the operand address and operation of that instruction. So there are basically 5 types of the addressing mode. First one is immediate addressing mode, second direct addressing mode, third indirect addressing mode, and fourth is register addressing mode, and fifth is register indirect addressing mode. So we learn one by one here. Immediate addressing mode. It is the simplest form of the addressing, that is known immediate addressing. in which the operand is actually present in the instruction. So, we know that an instruction is basically denoted by the two part. First one is opcode and second one is operand. And basically, in the case of immediate addressing, the data or operand is already exist in the operand part of the instruction. This mode can be used to define and use the content or set initially value of variables. The advantage of immediate addressing mode is that no memory references other than the instruction phase is required to obtain operand. And disadvantage is that the design of the number is restricted to the size of address field, which in most instruction set is small compared with the word length. Next addressing mode is direct addressing mode. In this addressing mode, basically we have the address of data in the address part of the instruction. Using this address part, we basically search in the memory address, and in this memory address we basically find the operand. So, a very simple form of addressing is direct addressing, in which the address field contain the effective address of operand. It requires only one addressing reference and no special calculation. Next addressing mode is indirect addressing mode. In this addressing mode, basically the operand field does not have the direct address of the operand. It holds basically the address of a memory, and this again memory address hold the address of the operand. So basically this addressing mode is performed in two cycles. Due to this reason, it is known as an indirect addressing mode. With direct addressing, the length of the address field is actually less than the word length, thus limiting the address range. One solution is that we have the address field refer to the address of a word in memory, which in turn contain full length address of the operand. This is known as a indirect addressing mode. Next addressing mode is register addressing mode. The register addressing mode is similar to direct addressing mode. The only difference is that address field refer to the register rather than main memory address. So the advantage of register addressing are that only small address field is needed in the instructions and no memory reference is required. And this disadvantage is that register addressing is that address space is very limited. Next addressing mode is the register indirect addressing mode. Register indirect addressing mode is again performed in two cycles. Register indirect addressing is similar to indirect addressing, except that address field refer to the register instead of the memory locations. It requires only one memory reference and no special calculation for the effective address. Register indirect address use one less memory reference than indirect addressing mode. Because the first information is available in register, which is nothing but memory address, from that memory location we use that to get the data or information in the general register. Access is much faster than memory access. Today our lecture finished. Thank you.